Hi, my name is Jared Hoteling, and today I'll be talking about cognitive processes and dynamic decision making. So, whether it's planning for our retirement, managing the long term health of a medical patient, or making adaptive decisions in a combat environment, a lot of the important decisions that we face, they aren't just risky or uncertain or ambiguous, but they're also complex. And a feature I'll focus on today is that these choice scenarios are sometimes dynamic. So the scenarios unfold across a sequence of interdependent events, some of which we can control, others that we can't. And I'll define dynamic decision making as a situation where the outcomes that we receive come from a series of interrelated choices and events. And an important feature of this type of problem is that what you do now will affect what you can do in the future. So with dynamic decision-making research, we're trying to take decisions out of the vacuum, so to speak, looking at interdependent choices in these complex environments. And what's nice about this is that it gives us new insights into things like how people search for information, how they plan ahead, and what sort of simplification strategies they might be using. And we can represent dynamic decisions in terms of decision trees, where you might imagine a real world scenario where you have an office worker trying to decide whether to ask his boss for a raise or not. So with these trees, we have decision nodes. These are points where you as the decision maker decide whether to move left or right. There are chance nodes where some event outside of your control determines which direction you move. And then there are outcome nodes at the end of each branch representing some punishment or reward, some outcome. And if we quantify the decision tree like this and assign points to every outcome and probabilities to every chance node, then we can apply our normative model of backward induction. And what backward induction says is that you should begin at the end of the tree. And the first thing you should do is use these probabilities to compute expected values for each of these chance nodes. And once you do that, you move up to the final decision stage and you say, okay, if I find myself here in the future, I'm going to choose 31 because it's greater than 17, which means I can kind of prune that branch and ignore it. I can do the same thing on the right side. Since I know what I'm going to choose in the future, I can carry those values up to the decision node. Now I move up another level and I can use these probabilities to compute an expected value for this chance node. And now I'm at the top of the tree and I have a choice between 29 and 7. And so backward induction says I should choose 29, and then I should execute my plan exactly how I've made it. So I should move left if I end up here, and I should move right if I end up here. Now, one traditional approach to studying dynamic decision making has been to focus on these normative theories because they provide formal axioms. We can compare behavior to this well understood standard, and then we can use this as a starting point for developing descriptive theories. And under this experimental approach, people use very simplified experimental designs that are meant to test these axioms kind of directly. And um, one of the important axioms here is that of dynamic consistency, which says you should follow through on your plan. And remember, these calculations are dependent on your future decisions. So if you don't follow through on them, you undermine the optimality of those choices. Another axiom is that of consequential consistency, which says only the future consequences should affect us. And this is essentially a byproduct of working backwards through the tree and not having access to the past. And a classic example of this approach of testing rational axioms is shown by the 2000 paper by Bussmeier and colleagues, where they were testing for people's adherence to dynamic and consequential consistency. And what they did was compare choices across a couple different conditions. So in a planning condition, they asked you, before you begin solving this tree, what are you going to do if you end up at this final decision node? And then they can compare that to a situation where you're not asked for an explicit plan. You just work your way through the tree and they observe what you do at D. And then they can compare that to a third condition where you don't see the decision tree. You're just given this isolated choice between G and S, and we see what you do. And by and large, what they find is that people are robustly violating the axioms of backward induction. Now, you can contrast that axiom-focused approach to one that's focused on characterizing individual differences. And here, the motivation is that we'd like to know how people's strategies differ from one another. And in order to do that, we're going to make minimal assumptions and use simplified models that gloss over a lot of the underlying processes. So this work is well characterized by the work of John Hay and his colleagues, where they're trying to classify people by qualitative types. So they want to distinguish between broad classes of theories, for example, people who use backward induction to plan ahead versus people who don't plan ahead and are characterized as forward workers. So what's often used in these scenarios is true and error modeling. So this is part of the multinomial processing tree family of models. And the idea is that it considers the entire pattern of choices in order to avoid some well-documented aggregation fallacies. And it's going to make very minimal assumptions. For example, it's going to assume that people satisfy dominance, which is to say, if you have a decision node like this, where the gamble on the left stochastically dominates the gamble on the right, then we assume that people are going to detect this, and when they do, they will choose to move left. And there's some probability that they move right that's characterized by this constant trembling hand error mechanism. And then we can use these assumptions to classify people as either backward workers or forward workers. And we can do it in a way that's kind of uncontroversial. It doesn't involve buying into a lot of assumptions of a model. And what's often used in these situations are diagnostic decision trees, where you might have a tree like this, where it turns out at every one of these second stage decision nodes, one of these gambles stochastically dominates the other one. So if you're someone who plans ahead, then you're going to prune all of the branches on the right. You'll carry these expected values up to the decision nodes. And if you do that, then you will get a higher expected value if you move left at the top of the tree than if you move right. But if you don't plan ahead, if instead you're what Hay and his colleagues would call a forward worker, then you sort of just treat everything on the left as one big lottery and everything on the right as one big lottery. And if that's the case, then it turns out that moving right has higher expected value than moving left. And so they use this sort of strategy to categorize people as planners and non-planners. And they find that, for example, around 60% of people are planning ahead and the remaining people are not. Or in an experiment where they have three layers of decision nodes, they find that some people are using backward induction. Some people make one irrational decision, then backward induce from there, whereas other people are just kind of barreling forward using, sort of ignoring the future decisions that they'll be making. All right, so I'd like to contrast those two traditions with a newer one that's focused on cognitive modeling, where we're going to try to understand people's behavior in terms of cognitive constructs. And I would propose that this combines some of the strengths of these other approaches. In one, it appeals to generality. We have a general purpose model that can be applied in many contexts, but it also provides us this formal way of representing different decision strategies. So we can classify individuals, but now in terms of their cognitive mechanisms rather than their behavior. And the kind of inspiration for this comes from decision field theory, which is a sequential sampling model that's been applied across many, many different domains. And the basic idea here is that you make a decision, say, between options A and B, by engaging in this noisy, attention-driven sequential sampling process. So you're thinking about the features of A and the features of B. Sometimes that causes your preference state to move in one direction or move in the other until eventually your preference gets strong enough that you hit one of these decision thresholds representing the amount of evidence required to make a choice. And so I've extended this model to apply to dynamic decision-making situations. And what I sort of appeal to is the concept of mental simulation, which it turns out is just a sort of straightforward extension of the sequential sampling assumptions of DFTP. And using this framework, I can also represent individual differences within a kind of unified and well-validated computational framework. So let me give you a sense of how simulation works in the model. So if we return to our office worker, what we imagine is that when you're at the top of the tree trying to decide what to do, you simulate what's going to happen. So you say, okay, if I ask for a raise, I think my boss will probably say yes. And if he says yes, I think I'll choose to take the company stock. And the stock market's been doing really well. So I think that's going to result in a really good outcome. And then you simulate what happens if you don't ask for a raise, and that's pretty straightforward. And then you compare those two outcomes, and in that case, you're probably going to take a step towards asking for a raise. But then at the next moment in time, your attention might switch to different features, and now you say, well, you know, if I ask for a raise, my boss might actually say no. And if he says no, I think I might need to leave and look for a new job. And the job market's not so great these days. So that might result in a pretty bad outcome. And so now you would compare that outcome to what you get if you don't ask for a raise, and your preference will probably step in the other direction. And so what we imagine is that you're deliberating, you're tracing different paths through the tree according to your subjective understanding of their likelihood. Your preference state is evolving in this noisy fashion until eventually you hit one of these decision thresholds and you decide to, in this case, ask for a raise. So unlike backward induction, the story we're telling here is one that's entirely forward-working. Okay, we're not starting in the future and thinking backwards, we're looking towards the future. We're planning, but we're doing it kind of on the fly. As you trace a path through the tree and you hit one of these decision nodes, you just imagine what you're going to do, or you predict what you're going to do. You don't make a hard and fast commitment. All right, so now I'd like to talk about a new study that I've done in collaboration with David Kellen at Syracuse and Will Dang at Illinois. And the idea here is that we're interested in whether or not people are planning ahead. And we're going to take an approach that's more typical of contemporary experimental psychology. So we're going to collect more data at the individual level, and we're going to get multiple repetitions of each type of trial, which is important for our true and error modeling. And then we're going to apply both true and error models to the data, as well as cognitive models that are built within the DFTP framework. And we've got 40 different trials and 3 types of trials. So we have full trees that look like this, and they all have that dominant structure that I explained previously. Then we have half trees where we take half of the chance nodes and we collapse them down to a sure thing that has the expected value of the gamble. And then we have single stage trees, which are a nice sort of comparison, because this is what, say, Hay and colleagues think that the non-planners are treating the decision trees as. So I'm showing you here results from an experiment with 50 people. I've got the proportion of choices, of maximizing choices here on the vertical. So this is proportion of choices that conform to the predictions of backward induction. And what you can see if we focus on decision node 2, so the final decisions that people make in the trees, we see very high levels of maximization. So each of these dots is an individual mean. The black bar is the group mean, and you see that people are maximizing at greater than 90%. Same thing in the single stage trees, people choose the higher expected value option. But if we take a look at what people do at decision node 1 at the top of the tree, we see much lower levels of maximization. We also see high levels of variability. So there are these people here who are making all of their choices in accordance with backward induction, whereas there are people down here who are 100% of the time making a choice that conflicts with backward induction. So we can apply our true and error modeling to this data, and the idea here is that we can use this model to separate out the effects of random errors from differences in preferences. And we can do this in a kind of uncontroversial way where you don't need to necessarily buy into the assumptions of DFT. And what we find when we do this is that if we allow we find that somewhere between 30 to 50% of people are best characterized as backward induction users, whereas the remaining people are best characterized as forward workers. And the reason that there's a range here is that we actually allow for the possibility that people switch their strategy halfway through the experiment. So what we find is that at the beginning of the experiment, about 30% of people are using backward induction, whereas by the end of the experiment, about half of people are using backward induction. Now we can also apply our cognitive models to this data set. And to do this, we're going to take the DFT framework and we'll modify it to represent different decision strategies. And then we'll use model selection to test different hypotheses, like are people planning ahead? Are people using a particular simplification strategy? So all of the versions of DFTP share that mental simulation mechanism. And then there are a couple free parameters that are worth attending to. So we have evidence thresholds, we have a sampling bias, and we have daydreaming. So the way this works is that when you're deliberating over one of these problems, we use this delta parameter, the sampling bias parameter, to account for the fact that when you reach one of these chance nodes, you may not simulate it according to the true objective probability. Instead, you might have a bias in terms of the extremity of the outcome. So if you reach this chance node, you might have a higher probability of simulating this 16-point outcome because it's more extreme and it's more attention grabbing than this 8-point outcome, which is more in the center of the distribution. In addition to that, we imagine that there's a possibility that your mind might wander. So we have this daydreaming mechanism that says on every time step, there's some possibility that instead of simulating an event from the tree, you daydream and imagine some other outcome. And we represent that as just uniformly drawing from a uniform distribution between the maximum and the minimum value in the experiment. So basically, you imagine a kind of a legal outcome in the universe of outcomes that you're experiencing. And then critically, we have versions of the model that use two different threshold parameters, one for planning ahead and another for making a final choice. So the idea is that when you're at the top of the tree and you have all this information you need to process, you might set a relatively low threshold. Only engage in a handful of simulations. That might also be the threshold you use when you're simulating your future choice. You just run a quick and dirty simulation of what will happen here. But then after you make your first choice and you end up at one of these final decision nodes, you might raise your threshold, engage in more simulations, and make a more careful and more rational decision. And then we can compare those versions of the model to versions that don't plan ahead at all. So what we do here is that we imagine when you're at the top of the tree and you're thinking ahead, as you simulate and reach one of these future decision nodes, you don't predict the choice you're going to make in the future. Instead, you treat this like it's some random event outside of your control, which we just model as kind of flipping a coin and having a 50-50 probability of simulating left versus right. Okay, so we use cross-validation to test these models. So we use a fourfold procedure where we calibrate the model on 75% of responses, then we generalize to the remaining 8 trials, and we rotate through the data 4 times, and then we calculate the mean generalized log likelihood for each model and use this as its goodness of fit. And so we can organize our results in this 2x2 matrix here, where we have DFT1, which is a one threshold model that is consistent in its processing across the stages, and it does plan ahead. And then we have DFT2, which is a planning model that uses 2 different decision thresholds and changes the way it processes across stages. And then we have the non-planning versions of those 2 models that replace the future decision node with a random coin flip. And so if we look at the number of participants who are best fit by each model according to cross-validation, we see that around 14% of people are best fit by DFT1, another 19 are best fit by DFT2, 7 people are best fit by the non-planning version of DFT1, and 17 people are best fit by the non-planning version of DFT2. So we see about roughly equal numbers of people are not planning compared to planning. And just to kind of compare that to our true and error modeling, this is somewhat similar to what we see in this case. Now, I'd also like to show that the model produces good qualitative fits to the data. I'd be happy to spend some time working through these graphs in the question period, but in my remaining time, I just want to give a sense of some additional insights we can get by examining the parameters that we estimate. So we see that people are changing their processing across stages. So if we take a look at the value of the decision thresholds across the 2 stages, we see that people have a relatively low threshold when they're planning and simulating their future decisions. So they're making kind of quick and dirty decisions at the top of the tree. But then at the final decision node, we see that parameter values have increased quite a bit, showing that people are more variable, but they're also being quite a bit more careful. We also see some interesting effects when we look at the biased sampling parameter, with the majority of people showing a value greater than 0.5, indicating greater attention being paid to extreme outcomes rather than more common ones. All right, so to quickly wrap up, we see that with dynamic decision-making research, we're able to examine decisions outside of the vacuum of the classic kind of static decision scenarios. We can examine them in richer, more complex and naturalistic environments. And by applying the techniques of cognitive modeling, we're able to draw from the strengths of both traditional approaches to the study of dynamic decision-making, where we get a generalizable framework that makes testable predictions across a lot of different contexts and provides us with tools for accounting for heterogeneity within a unified computational framework. And we also are provided some deeper psychological insights into, say, the cognitive mechanisms that produce choices. And with decision field theory planning, we have this unified framework where we can conceptualize differences in dynamic decision-making using psychological constructs and cognitive mechanisms. So with that, I'd like to thank my collaborators, David Kellen and Will Dang, as well as everyone in the Cognitive Decision-Making Lab here at Illinois. And thank you very much for your attention.